So we're going to be looking at horizontal circles. And we talked a couple of days ago, I showed you a Neil deGrasse Tyson video talking a little bit about the Coriolis effect. He called it the Coriolis force. I don't like the word force because that means, oh, it's measured in newtons. It's not. It's an effect of, it appears as though there's a force. And you'll see what I mean. Put your pencils down and look up. Oh, don't think I want that one. I think it's the Coriolis effect, that one.
What's going on here? Every time I throw the ball straight, it seems to bend to the side. No matter what I throw, no matter how straight I throw it, the ball seems to be curving. Maybe it has something to do with this. That whole time, I was spinning, which is why it looks like I'm about to puke. That curve is created by the Coriolis effect. You may have heard that it makes water in the bathtub spiral down the drain a certain way, or that it determines the way a toilet flushes. That's actually wrong. Those are not caused by the Coriolis effect. But the Coriolis effect is what makes hurricanes spin, and it's the reason why Jupiter's Great Red Spot is spinning the way that it is. So what is the Coriolis effect? Well, it's what happens when objects moving in a straight line appear to curve because you are rotating. And it affects all kinds of things. It bends the paths of missiles and sniper shots. But how does it work, and how does it create hurricanes? Right now, it seems like the ball's curving. But let's take a look at what's really happening. My friends and I put together this little experiment using a sort of spinning seesaw.
This is why, if you ever get a chance to play catch on a merry-go-round, you gotta try it.
Here, the camera's standing still. It's just hanging from the ceiling. And watch what happens. From the moment the ball leaves my hand, it's just going straight. Let's watch that again, frame by frame.
Like a normal throw, because Newton's first kicks in once you let it go, okay?
Keep your eye on the ball. You can see it travels in a perfectly straight line. But what if you're spinning with the seesaw? Look at what happens when you rotate the footage so the seesaw stays sideways and everything moves around it. Now let's follow the path of the ball again, but from this new perspective. The trajectory looks completely different. Now let's watch this one frame by frame. From this rotating perspective, it totally looks like the ball is curving. That's crazy because you already saw that exact same throw. Watch it again on the left. The ball is going straight, but on the right, when you're rotating with the seesaw, the ball really looks like it's curving. You might be thinking, why should I care? I don't spend a lot of time on a spinning seesaw or on a merry-go-round. But you kind of are on a merry-go-round. The Earth is constantly spinning. Have you ever seen someone in a movie making fine adjustments on their gun? Well, one effect they're correcting for is the Coriolis effect. The longest sniper shot, which was over 3,000 yards, would have had to correct for a 1-foot deviation due to the Coriolis effect. So how does the Coriolis effect create hurricanes? Hurricanes form when air rushes from all directions into a low-pressure region. So imagine there's a low-pressure region between the two of us. Air is going to rush toward the center. Let's see what that looks like from space, from our camera that's hanging from the ceiling. It's not spinning, so the air, or in this case the balls, are clearly going in a straight line. But if you're rotating with the Earth, or with the seesaw, you'll see the air bend to the right. In the northern hemisphere, this creates hurricanes with counterclockwise spirals. In the southern hemisphere, it does the opposite. It creates hurricanes with clockwise spirals. This storm on Jupiter, which is actually bigger than the Earth itself, has been spinning for at least 200 years, largely due to the Coriolis effect. So when you're in a rotating frame, the Coriolis effect seems to exert a very real force on objects. But there is no force.
That's why I didn't like it when Mr. Tyson said Coriolis force. It's an effect. There's no unbalanced force acting on it. But it's pretty dramatic.
What you observe is just a result of your perspective. And you might be wondering, if this is simply a product of your frame of reference, then could other forces like gravity or electromagnetism also just be products of your frame of reference? of where we live in the universe or in the multiverse? For more on that, check out our video, Do We Live in the Multiverse? There are talking fish. And if you want to find out when new episodes come...
Okay. Good YouTube channel, by the way, that one there. Imagine you are in a car going around a corner, making a left turn. What's the direction of your acceleration? And what's the direction of the force that acts on you? You know what? This looks like it's multiple choice. In fact, it looks like it's one of those two-column multiple choice questions. I'm not going to be foolish and try reading across. I'm going to read vertically and use check marks and X's. So if I'm going around in a circle, turning left, what's the direction of the acceleration? Inwards or outwards? I would go yes, yes, no, no. What's the direction of the net force? Inwards or outwards? I would go yes, no, and now I zoom out and it's obvious. Danica, what's the correct answer? The one that has two check marks next to it. What's the correct answer? Has to be. You've already seen some questions like that, I think, on your test this year. You'll see more. Do yourself a favor. For a two-column question like that, read vertically one column at a time. Otherwise, you're having to track two answers in your brain. Explain your answer using relevant principles of physics. I think I have. We've said that if you're moving in a circle, it must be an unbalanced force towards the center. So I'm not going to worry about the explanation. Example 1 says this. A test tube rotates with a period of 9.9 times 10 to the negative 4 seconds. What's the centripetal force on a 1.8 times 10 to the negative 9 amoeba at the bottom of the test tube? The bottom of the test tube rotates in a circle of radius 0.15 meters. Okay. Mason, what's this question asking me to find? The what force? Read carefully. The what force? The what force? The what force? In the same way as in the forces unit when it said net force, you could go straight to F equals ma, no free body diagram. If it says find the centripetal force, because that's the right side of the equation, you can go straight to Fc equals mac. No free body diagram required. Which version of A am I going to use? The one with the V in it or the one with the T in it? This time they gave me the rotational period. So now it's going to be m4 pi squared r over t squared. Don't forget the m. A common mistake is kids will say, isn't that the net force? Because it looks so complicated. It must be a force. It's an acceleration. F equals ma. What's the mass? 1.8 times 10 to the negative 9. 4 pi squared 0.15 all over 9.9 times 10 to the negative 4 squared. Every one of you must try typing this in because some of your calculators might give you an obscure glitch here. But I don't know which models do it. It's not consistent. If you get an error, let me know. I got 0.010875. Some of you might get an error, although maybe as calculators are getting a bit more modern, that error is vanishing. Did anybody get an error? Okay. Some calculators, it wouldn't let you put a 4 and a pi squared without putting the times sign between them. It wouldn't let you put a coefficient in front of the pi squared. The software didn't know what to do. So that's why. Am I right? Is that what you got? Okay. I could write it in scientific notation, but it's only one decimal after. You know what? I'm going to go 0.0109 newtons. Is that a big force? It's massive for that amoeba. How could I find the acceleration if that's a force? If F equals what? How can I get the A by itself? On your calculator, divide by the mass. Just to see what the actual acceleration here is. I get that. How many G's is that? Divide by 9.8. That may have seemed like a small force. I'm telling that amoeba got pulverized. That's what a centrifuge does. It separates organelles and parts of cells out because they all have slightly different masses and inertia. They end up being spread out along the edge of the test tube. Okay? This pulverized it. That's over 500,000 G's. That'll do it. Example 2. I kind of like example 2, but it's too easy. I kind of like example 2, but it's too easy. But we'll start here. Here is a horizontal circle. Paige, did that work okay on your calculator?
No.
Okay. A car is approaching a circular turn that has a radius of 60 meters. If the coefficient of friction between the car and the pavement is 0.45, what's the maximum speed that the car can safely travel through the turn? What's this question asking me to find, Arsh? A V. I don't think a VF because I don't really know if there's a VI. What path are we tracing out? Psst. What path are we tracing out? This is going to be a job for a free body diagram. The really tricky part is what free body diagram, how to draw it. Don't write this down, but look up. Taryn, look up. I see some kids, they think, okay, here's the car going around a corner. I'll draw a vertical looking down at it, bird's eye view. And so they go, there's the car. What are the forces acting on it? Get the oh, that's into the page. And normal force would be out of the, a vertical doesn't work. What does work is a front view. I'm going to draw it. I don't want you to draw it. I want you to watch how I draw it. Then you're going to recreate it. So my free body diagram is going to be a front view. I'm going to have the road right here, and I'll put a little axle right there to show that's the center of rotation. And I'll even do that to say we're going around a corner. And I draw a very stylized car. I draw 2 tires, headlights, and a roof. This is a way better free body diagram. How come? What are the forces acting on it? Get the obvious one. Is it sinking into the ground like quicksand? Is it, what else? And then Arsh, what path is this car tracing out? Where must there be an unbalanced force pointing then? Toward the? I know there has to be a force there. What force is that? FC never appears on my free body diagram. That's silly. I told you, it never shows up on my free body diagram. What force is that? Taryn, you're right. Darn right, of course. You can't go around corners on ice. It's friction. That's your free body diagram. So you can write that down. You can draw the car if you want, or you can just put in the arrows. But I usually draw the car because, hey, I get to draw a little toy car. Top view free body diagram for a car going around a corner is yucky. Front view, having it come out of the page towards you, much better. Who's winning? Friction toward the center. Who's losing? It's a trick question. Who's losing? What's that going to equal? MAC, because we're moving in a circle. Arch friction is what times what? I don't know the normal force. Oh, but look. Another force the same size as the normal force. What? Equals M. Which version of A am I going to use? So you ready? What did they ask me to find? No. I specifically didn't use the word velocity. I used a different word. Okay, speed. Oh, I'm going to use the one that's got the speed in it. Which one? On your formula sheet, which version of A? More specific, exactly tell me what to write. We're in the circular motion section, front page. Okay, so we're going to try that again. You figured out where we are? You way overcomplicated that. Which version of AC am I going to use? Well, they asked for or mentioned speed, so I'll use the one with the V in it. Not velocity, by the way, because the direction is, I can't ask you to find that. We'd have to get a direction. That's always changing. So I'm going to use the V squared over R. Good. Oh! Can small cars and big trucks go on these same roads? Why? Well, that's convenient. Otherwise, we'd have to build separate infrastructures for different mass vehicles. What are we trying to find? How would I get that by itself? Hello, my old friend. I get the square root of GER. Okay, mu GER. I said sometimes you get something in front of it, but I got my square root of GER. I probably did this right. Yeah, that's the maximum safe speed going around a corner. I don't know. Radius is 60 meters. And make sure you took the square root. $16.3, or in kilometers per hour, 58. So you could do that. Now, if you took this corner at that speed, you would not be comfortable. You would be able to feel through the steering wheel that your wheels were ready to slip, that you were ready to go into a skid and start skidding sideways, skidding off the curb. So you would never take it this fast. In fact, that's not what we would post. We would probably divide that in two or maybe even more than that, because we also have to take into account when it rains, mu gets smaller. And we also have to take into account that drivers are really, well, they're stupid. They just are. Anyways, 16.3 meters per second. As far as I'm concerned, for a car going around a corner, there are, look up, 1 mu, 2 g, 3 v, 4 r. There are 4 variables. I can give you any 3, find the 4th. Yeah, I can even ask you to find g if I put you on a strange planet. You could say we have a car going around a corner on planet Duick. What's g? Okay. Is that all right? So in your home, I'm not going to do every single example, but as far as I'm concerned, that's now fair game. The key is, can you draw the free body diagram, and then you realize friction is what's pushing us in a corner. Example 3, an empty swing on an amusement park ride has a mass of 10 kilograms. How many of you have ever been on the swing ride at an amusement park? Okay. At Playland, it's called the Wave Swinger, I think, or something like that. Often when a carnival comes by, they'll have one there too. Okay. If the swing has a kinetic energy of 460 joules, what is the centripetal force on the swing? Amrit, what's this asking me to find? The what force? The what force? You know what? This is just like when it said the net force. I don't need to do no stinking free body diagram. I can go straight to saying Fc equals MAC. Which version of A am I going to use, folks? The one with the V in it or the one with the T in it? Not so obvious this time. How did you figure out the one with the V in it? kinetic energy has a V. Okay, so I'm going to go like this. I'm going to write Fc equals mv squared over r, and then I'm going to hit pause, and I'm going to go see if I can do something with that kinetic energy. I'll do that down here. Apparently, the kinetic energy is a half mv squared. I remember that. Didn't even need to look it up. I'm going to get the v by itself. Actually, wait. Why don't I get the v squared by itself, since it's a v squared here? Because otherwise, I would take the square root and then just square the thing later. I could plug in numbers, by the way, but I'm always interested, can I do it algebraically and spot a pattern? So I'm going to say v squared is 2 times the kinetic energy divided by the mass. I think that's right. And I'm going to plug that in right here. And I want you to notice something kind of cool happens. I get Fc equals m over r 2 Ke divided by the mass. What? Have you been on the wave swinger before? You're right. Have you been on the musical swing? Would an empty swing and a full swing out to the same angle, or will one swing out higher? What did you just tell me? So, will an empty swing out higher, the same, or lower? What did you just tell me? Same. That's important. If that wasn't the case, if there was an empty swing on the inside of you, it would smash into you. Okay? Watch it next time. Now, it's not quite perfect because your body provides some air resistance. One with a person will be a few degrees further in, but pretty close. Certainly, we're not worried about empty swings on the inside smashing into people on the outside because they swung out higher. Hope your next trip to the amusement park, you notice some more things. I hope I made your playland funner for you. So it's just going to be 2 times Ke divided by r. Okay. 2 times 460 divided by, from the picture, 7. Now, if you're not sure if the mass cancels, then don't plug it in. You'll still get the same answer. You'll have just done some more typing. If it does cancel, anywhere that you multiplied by 10, later on you would have divided by 10. No problem. Oh, and Danica, can little kids and grown-ups go on this ride? Yes. $131? Units. Pardon me? Oh, okay. I like example 4, I like example 4, I like example 4. Example 4 is a nice question. Remember I said the car going around the corner was a little on the easy side? This one's got a little more teeth to it. It says this. A car can travel without slipping at a maximum speed of 22 meters per second in a circular path of radius 72 on a dry horizontal surface. But when it rains, the coefficient of friction is reduced to 1/2 of its original value. What's the maximum safe speed when it rains? You know, I've done enough of these. I'll bet you if we start solving this for when it rains, we'll get partway through and we'll go, ugh, I need something else. I bet you I'll have to now analyze it when it's dry and I can find that something else. So I'm going to do this. And over here on the left, I'm going to say, when it rains, when it's dry. Braden, what's this asking me to find? I think I'm going to do a free body diagram. It's going to be that same car one. I'm going to do it, I think, right here. So it's going to be car going around a corner, and we had Oh, Mr. Dewick, you have to draw your picture of the car. I do. So we have the tires, headlights, there's the roof. Okay. Gravity down, normal force, friction. Cool. Braden, what's my equation? Friction is what times what? I don't know the normal force. Oh, but look. So I think my next line, I would say mu mg equals m, and then I would cleverly plug in the v squared over r because it looks like they're asking for the speed. Braden, can big trucks and small cars go on this same road? Well, that's convenient. What are we trying to find? Do I know r? Do I know g? Do I know mu? So I'm going to get the v by itself. I'm going to say it's equal to mu gur. You know what? Mu, when it's raining, I'm going to put an r as a subscript underneath this mu so I don't mix it up. Because I think now what I'm going to do is I'm going to repeat this question for when it's dry. I'm going to find mu, and then how does that mu when it's dry help me find the coefficient of friction when it's wet? I'll divide by 2. Okay. I'm not going to redo the free body diagram. I think it's the same. In fact, I'm pretty sure I'm going to end up with, when it's dry, mu mg equals mv squared over r. But this mu is when it's dry. I'll put a D for dry. Braden, when it's dry, can little cars and big trucks still drive on the same roads? Oh, that's convenient. Now I'm going to get the mu by itself. Divide by G, yes? Mu on the dry road is going to be V squared over Gur. What was V? 22? Don't forget the squared. All over 9.8 times, was it 72? 72. Hope I get a reasonable answer. I get, okay, yeah, 0.686 units. Oh, none? Okay. Now, I'm going to go divide by 2, answer button divided by 2, and I get 0.343. I'm going to say mu raining equals, I'm going to write 0.343, but you know I'm using my answer button, right? Because now I can solve for V when it's wet. 0.343 times 9.8 times 72. Answer button times 9.8 times 72. And then I would say, wow, that seems a little fast. And then I would clue in, yeah, square root. And I get 15.6 meters per second. Again, if you were actually taking this corner at this speed or even close to this speed, you could feel through your body and through the steering wheel in your hands that your car was about to slip off the road. You would not be comfortable driving this fast. You would slow down. Little technical comment on turning a car. So when you're turning a car, Paige, I've told you that friction is what's pushing you in a circle. It's what's pointing inwards. Now, why is that? When you turn your front wheels to turn the car, Newton's first says the car wants to keep going straight. But when you turn your wheels like this, they actually apply a force against the road outwards from the circle. Forces come in. If your tires apply a force outwards, what does the road do? Apply a force on the tires and the car inwards. That's really what's going on. It's a combination of Newton's first, your car wants to keep going straight. Newton's third, forces come in pairs. Okay? And again, friction then is perpendicular to the direction the car is moving, towards the center, because the car is moving tangent perpendicular to the radius. This is because turning friction is static friction, and static friction isn't always opposite to motion like kinetic friction is. It's at right angles to it. So in horizontal circles, the vertical forces will be balanced. You're not sinking into the ground like quicksand. You're not flying here like Superman. The net inwards force is going to be MAC, which is mv squared over r, or m4 pi squared r over t squared, depending on whether they give you or ask for speed or period. Okay. Put your pencils down and look up.
This is the Royal Air Force Training Centrifuge at Farnborough, and the team here are going to push me as far as they are allowed to push a civilian.
The centrifuge has been here since 1955. The device was originally installed for research purposes, although these days it's used for training as much as it is for research. What it does is recreate the forces that you feel in an aircraft. For our routine pilot training, the first time pilots go on the centrifuge, we expect them to get up to 5G without a G suit, and then up to 7G with an anti-G suit.
Now, I'm not taking a significant risk here. I'm healthy, I've pulled a few Gs before, and the human body can take this. And the reason we know that is because in the 1950s, the US Air Force used rocket sleds to push volunteers to incredible speeds.
You might remember Colonel John Stapp. We saw some videos last year about him.
But that rocket-powered acceleration wasn't the dangerous or even the really high G part of the test. See, high G acceleration takes a lot of incredibly expensive rockets or a big old centrifuge like this. But high G deceleration, all you need for that is a wall. Or for something less destructive, like rocket sleds, you use scoops dropped down into a water trough. US Air Flight Surgeon John Stapp, aboard the rocket sled Sonic Wind No. 1, holds the record for the highest sustained G-force anyone has ever voluntarily endured, 25 G for 1.1 seconds, with a brief peak over 46 G. And he was badly injured, but he survived and he recovered, and he lived to the age of 89. The human body is an incredible thing, particularly because we didn't evolve for this.
G-tolerance is something that's innate in all of us. Some of us have high G-tolerance, some of us have low G-tolerance. Over the years, people's G-tolerance doesn't really adapt. Any shortfall in G-tolerance has really got to be made up by physical exertion in the G-straining manoeuvre.
What the centrifuge doesn't have is much jerk. And jerk is a technical term. In the same way that acceleration is the rate of change of speed, jerk is the rate of change of acceleration.
Or if you're a calculus student, you may have learned the derivative of distance is velocity. The derivative of velocity is acceleration. The derivative of acceleration is jerk, how fast the acceleration is changing. And then if you're a nerd, you may have asked, what's the derivative of jerk? It's called snap. Derivative of snap is called crackle. Derivative of crackle is called pop. We have a sense of humor. We name them that. But also, there's very few, if any, situations where you actually have a seventh derivative that actually exists. So this is both going to show us G's and jerks.
And because it takes time to spin up and spin down, oh, here we go! Even though the acceleration is high, the jerk here is relatively low, about 1 G per second. Jerk is the difference between a rocket to space, which might take a couple of minutes to reach peak acceleration, and a fighter jet, where manoeuvres might change the G-force acting on you in a fraction of a second.
Or hitting a wall, where your acceleration would change incredibly rapidly.
And it can go further than that. You can measure the rate of change of jerk, which is called snap or jounce. The two derivatives after that are called crackle and pop, but they're not all that useful in the real world.
As we increase the G that Tom is exposed to, the blood's going to be pushed down into his feet, and he's going to have to work really hard to push that blood back up to feed oxygen to his brain to keep him conscious. And in real life, we would be expecting that person to be flying an aircraft whilst doing that.
I'm getting a little bit of grey out. I can't quite see.
We teach the anti-G straining manoeuvre, which composes of two separate parts. First of all, muscle tensing, so both the buttocks and the legs, squeezing the blood vessels to try and get the blood back up into the chest and the head.
Basically trying to make your face go red, but also doing that with your chest to keep the blood there.
But also the second part is a breathing manoeuvre, which increases the strain in the chest, directly increasing the blood pressure to the great vessels in the chest and keeping him conscious. And when you lose blood pressure to your head, you could even lose consciousness, and we term that G-induced loss of consciousness, or G-lock.
Blimey! I lost everything there. Wow!
G-lock in itself is not dangerous, but the real point is when you G-lock, you're flying an aircraft. So if you're not able to fly that aircraft, I'm sure you can appreciate that that is a real problem.
Because of John Stapp and all the volunteers like him that rode the rocket sleds, there is a lot of research into acceleration on the human body. How many Gs can be withstood for minutes at a time? How many Gs can be withstood for brief moments? And how many can be withstood with training that I clearly don't have? Rocket scientists and roller coaster designers use that data. But there's not much research into jerk, because how do you test it without also testing acceleration? Over on the Starship channel, I am not passing out pulling G's with the blade. I am in an unpowered glider somewhere over Oxfordshire with Bruce, my pilot and instructor behind me. Bruce, thank you very much. And I have a bottle of water with me. Now we're in level flight at the moment, so as you'd expect, the water in the bottle is about level. But watch what happens when we start to turn. Bruce, give us a, there we go, a bit of a turn to the left. That's a heck of a view. Now look at that. Have a look at the horizon line.
They're very tilted, but look at the water in the bottle. It's still level. What does that mean? It means your body can't feel that the plane is tilted. It means that your body feels a normal force straight down into the chair. Your body does not feel like you're leaning sideways right now. Even though you are leaning sideways, it feels you're vertical. This is very dangerous.
According to the camera, it's massively away from horizontal. But look at this bottle. The water level here is still flat. If you can't see the horizon, then as far as you're concerned, you're not in a turn. And look how fast we're going round.
If you were in the fog, you couldn't tell that you were turning. There was no way you could feel it if you had no instruments. What you might notice, when you turn a glider or an airplane, you start to lose altitude. So if you're in the fog and you don't realize that your plane is turning, you would notice that your plane is losing altitude. So what would you do if your plane is losing altitude? Pull, which tightens the turn even more. Now your plane is losing even more altitude. So what would you do if you're losing even more altitude? Which tightens this has a name, it's called the graveyard spiral. And many pilots have died because of it.
Now that's very strange, isn't it? But if you've ever been on a jetliner or an actual commercial aircraft, you'll know that. A commercial aircraft can do this kind of turn without slopping your in-flight meal or your drink all over the place. Thank you, Bruce. Let's go back to level. So what would happen if we couldn't see the horizon? Because there's some really weird sensory illusions that come into effect there. If you lose sight of the horizon and you've been turning for about 15-20 seconds, your ears, the balance centers of your brain, get used to it. The only difference you feel is a little bit of G-force, but that's really difficult to detect. And if all you've got to go on is what you think is down, well, the forces are adding up. So down is always going to be towards your feet, even if you're turning. And even a bottle of water or something isn't going to clue you in. So again, as we turn to the right, still straight here. So if we were a little bit higher, if we were under those quite scary clouds above us and we couldn't see, we wouldn't know if we were turning. And that's worrying. Because if you turn, you start to lose a little bit of altitude. And if you're starting to descend, if your altimeter says you're going down, and you think you're flying level, then you're going to pull up to try and keep your height together. In a turn, that just makes it worse. That just tightens the turn, and you go into something that is called the graveyard spiral, for obvious reasons. That is also the reason that we are not flying in cloud or at night.
You're going to accelerate to 100
Yep.
knots, pull up level, and then gradually pull up.
Oh boy, yep.
Here we go.
Oh boy. Don't freak out. Oh boy, oh boy, oh my, oh wow, oh wow. Bruce, thank you so much.
That was awesome.
Bruce is from the Edinburgh University Gliding Club. I also need to thank the Loughborough University Gliding Club and Alistair who brought me up here.
Has anybody ever done a loop in a glider or a plane? I haven't. It's on my list of things I really want to try. I have done a couple of times weightlessness in a propeller plane. So a couple of years ago on a Pro D-Day, my friend who teaches at SRT and I, we went to Surrey, and one of his former students had their pilot's license. So he did where he dove down, and we had about 5 seconds of weightlessness, and that was pretty cool. But I haven't done a loop yet. That's on my list. Okay. What's your homework? Oh, circular water slide. Sorry, I got one more. This one's short. What path is he tracing out? Where must the net force be? Toward the... What's applying the force? His arms. Now, because he's not used to having to pull to maintain his position, he would say something is pushing him out because he's having to apply a force. That's just his own body's inertia. But this is why so many of us think, oh, there must be a force pushing us out. It's because we're not used to having to apply the force to hold our position. He's going to wipe out shortly. Notice when he does wipe out, he does not fly straight out from the center. He goes tangent to the radius.
Don't go in there.
And he kind of manages to stick the landing. We'll give him full credit for that. Okay? So again, moving in a circle, there has to be an unbalanced force towards the center. His arms are what's applying that force. By the way, forces come in. So the rope is also feeling a force outwards. That's the centrifugal force. There will be some physicists who say there is a centrifugal force. It's not a mythical force. It is there. It is if you start looking at the frame of reference from the center, but we're not doing that. So I'm going to argue centrifugal with an F force. It's the non-existent force. It's centripetal towards the center. That's what's existing. Actually pretty good. He sticks the landing pretty good. Let's go at the right time. He knows he's going to move tangent to the radius, so he's clearly done this before. Okay. Now what's your homework? You can try number 1. This is a top view, not my favorite free body diagram, but I think gravity would be into the page, normal force would be out of the page. You know what? Tension is what's pulling you in a circle. So you can handle that. 2 is good. 3 is good. 4 is good. 5 is good. 6 is good. You've assigned everything so far. Yeah, I'm also going to assign 7, but I'm not going to assign number 8. Yeah. Thank me later. 9 is good. 10. I'll do 11, but I'll skip 12. 13 is good. 14 is good. 15, but I'll skip 16.